Welcome back to Larry's Classroom. Today we're going to learn about square roots. The square root of a number is a number when squared exactly equals the given number. For example, if we look for the square root of 25, well, we know that 25 is equal to 5 squared. So that would mean 5 is the square root of 25. We could write this 25, the square root of 25 equals 5 because five squared equals 25, as we've written down here. A few more examples here. The square root of 81. Well, what number can you think of that multiplied times itself or squared would be equal to 81? That would be 9. 9 times 9 is 81. Equals 9 because 9 squared, or we'll write that as 9 times 9 to kind of demonstrate what we're doing here, is equal to 81. Now we're going to do another descriptive example, square root. The square root of 0.16. Now you'll notice this number has two decimal places. Whatever number we multiply times itself to get a number with two decimal places will be a number with one decimal place, right? Well, that equals 0.4 in one decimal place, as you see, because 0.4 squared, which is equal to 0.4 times 0.4 is equal to 0.16. Here you see what I'm talking about in the decimal places. We had one decimal place. Well, here's two factors for one decimal place, each 1, 2. Adds up to 2, gives us a 0.16. If the square root, when we use this radical sign to indicate square root, if the square root of any number is equal to a whole number, that's a whole number a fraction, or a finite, which means non-repeating, comes to an end. Well, it can be repeating, but doesn't go on indefinitely. Finite decimal. Any number whose square root is a whole number, a fraction, or a finite decimal is what we call a perfect square. A few minutes ago we saw that 0.8, I don't know if we did that one or not, we had 0.4. 0.4 was equal to the square root of 0.16. Well, this is a finite decimal. You could also write that as a fraction, 4 over 10. And actually, any finite decimal can be expressed as a fraction. May not always be simple to find what that fraction is, but any finite decimal can be expressed as a fraction. Well, 0.4 squared equals 0.16, which basically says that 0.16 is a perfect square, which is the square of 0.04 squared, or 0.4 squared, or square of 0.4 actually. So we're gonna do some we're gonna put down some numbers. Actually, I'm gonna write down the numbers from 1 to 12. I'm gonna say x equals 1, 2, 3, 4, 5. Let's spread these out a little bit. Let's do this a little bit. We do x squared. Well, 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. That's why I want to do it this way, kind of get them spread out a little bit. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared, 64. 9 squared is 81. 10 squared is 100. 11 squared is 121. And 12 squared is 144. So what we've done here, we've written a number, and it's square. So all these numbers that we arrived at by squaring whole numbers are perfect squares. So everything down here is a perfect square. So I'm going to write perfect in front of that. Perfect squares. There are others, but this is a list of the perfect squares of the first 12 whole numbers. And as you saw a few minutes ago, that we did a perfect square of a decimal fraction. Another example, 1/3. If we square that, that equals 1 squared over 3 squared. 3 squared equals 1/9. So 1/9 is a perfect square. It's a perfect square of 1/3. And 1/3 would be equal in decimal to 0.333. At some point we'll put a bar indicate that it continues on forever. But this is still a finite. It's a finite decimal in that it repeats. It's not a infinite decimal in that it goes on forever and ever with no repeating pattern. So these are the first 12 whole numbers and their perfect squares. Here's an example of a fraction. Create a perfect square. The 1/9 is a perfect square because 1/3 times 1/3 equals 1/9. Here is the decimal representation of 1/3. So we're going to work on a few examples. So we're going to find a few square roots without using a calculator. We're going to here's the first example we're going to do. We're going to say that A, I don't need an A there. The square root of 16 over 25. Well, we can break this down and take the square root of the numerator and the denominator separately. Is the square root of 16 over the square root of 25. Now, you probably can see that these are both perfect squares, 16 and 25, without looking at this little chart we just made. But nonetheless, 16 is a perfect square. It's a perfect square of 4. So the square root of 16 is 4. 25 is a perfect square, so it's the square root, and it's the square root of its square root is 5. It's the perfect square of 5. So this fraction works out the square root of 16 over 25. We broke it into the numerator and denominator. We took the square root of the numerator, we took the square root of the denominator, and we found that the square root of the fraction 16 over 25 is equal to 4 times 5. Now if we want to check this out, we could go 4 times 5, and we can square this. This will double check that we did it right. Well, 4 squared is 16, 5 squared is 25. We're right back to what we started with. So we found that the square root of the 16 over 25 was 4/5. We squared 4/5 and found that it did equal 16 over 25, or 16/25. Let's do a couple more like this. Square root of 64 over 81. Again, we break it down, take the square root of the numerator and the denominator separately. Square root of 64, square root of 81. Well, square root of 64, there's our perfect square. It's 8. So we have 8 over the square root of 81. 81 is perfect square, and square root is 9. So there we have another example of a square root of a fraction where the numerator and denominator were perfect squares. We'll do one more like that. The square root of 1 over 100. Well, we break that down again to the numerator and the denominator like we did the last couple. Square root of 1 over the square root of 100. And of course you can see here that 1 squared is 1, so square root of 1 is 1. 10 squared is 10, so square root of 100 is 10. So basically it's 1 over 10. And we could write that as a decimal fraction if we so desire, which would be 0.01. That would be 1. No, we got that wrong here. 0.1. Yeah, that would be 1/10. And of course, if we'd have written it like this to start with, the square root of 0.01, 2 decimal places, its square root has 1 decimal place. 0.1 squared is equal to 0.01. Let's make that look like a 1, not a 7. And we probably know that 1/100th is the equivalent of 0.01 because here's the tenths place and the hundredths place. We've done a number of those. So square root is basically, square root is the inverse operation of squaring. When we did we'll do a few more of these. We're going to try to work them out without our calculator. Square root of 1.21. You can always punch it into your calculator, hit a number, hit the square root key, or hit the square key, hit a number, hit equals. I guess that's the way most calculators do it. Well, we know that 11 squared equals 121. We got that right up here, right? Well, that looks like that. The right number of decimal places and such. Or not the right digits, not the right number of decimal places. So we could also say that the square root of 121 equals 11. And how close we want to be here, but we have 2 decimal places. We need 1 decimal place in our answer. So basically what we're going to come down to is 1.21. The square root of that equals 1.1. The whole number thing works out. Then we have 2 decimal places there. We have to have 1 decimal place in our actual square root because that's 1.1 squared is equal to 1.1 times 1.1, which equals 1.21. We do the whole number part, 11 times 11 gives us a 121. We do the 2 decimal places. So square root undoes squaring. We squared here. So we can also write this, that the square root of 1.1 squared is equal to 1.1. The square root undoes that raising to the power 2 or squaring of the number. And we call this symbol, the square root symbol, we call it the radical sign. Underneath, or and the number inside is called the radicand. So here, let's do one more, 0.64. Here's the radical sign. Inside here, 0.64 is the radicand, the number which we are applying the radical to. Well, 64 is the square of 8, so it sounds like 8's going to be working out, but how many decimal places we got here? We got 2. So we need 1 decimal place here, which would be 0.8. So the square root of 0.64 equals 0.8. And if we take 0.8 and we square it, we end up 0.8 times 0.8, and that works out to 0.64. We multiply the whole numbers, 8 times 8, 64. We put the 2 decimal places, and we're there. It's good to kind of have these perfect squares in your mind somehow. You can always work them out, but the more you have them in your mind without easy access, the easier it'll be to do something. And we're going to look at the definition of square root, which we've talked about already, but we're going to make it a little more formal. Definition of square root. And basically it says, this is in cases where x is greater than 0 with positive square roots. Basically we say the square root of x squared is equal to square root of x squared, we'll put the whole thing in parentheses, is equal to x. So what we see happening here is this squaring of what's in there undoes the square rooting. No, gosh, there's no square here. This squaring here undoes the square root. Square root of x squared, well, we can say that the square root of x squared equals x, so we know that the square root of x squared equals x. And if a number is not a perfect square, then the square root is an infinite non-repeating decimal. Non-repeating, and put non-repeating in parentheses. And the reason I put the non-repeating here to separate from things like we talked about a little before, 0, 3. And we found that was, well, that was the square root of 1/9, but this is not the same as a number that doesn't ever repeat. And this is what we sometimes call an irrational number. I guess I don't think they really mean a crazy number, but it's a number that cannot be expressed as an integer divided by another integer. And of course, integers are 0, 1 minus 1, 2 minus 2, 3 minus 3, 4 minus 4, and so on. So an irrational number cannot be expressed as a ratio of two integers or as a fraction with an integer in the numerator and an integer in the denominator. Any number that doesn't repeat, you can easily put it over 1 now. You've expressed this as a fraction if it's not already expressed as a fraction. We're going to give you some examples of non-repeating numbers. The square root of 2. Well, when you put that in your calculator, 1.41423 5, 6, it'll go on forever, and no pattern will ever develop. So these kind of numbers, most of the time we approximate them, and here's the little approximately equal symbol, the wavy equal sign. If we rounded this to 4 decimal places, we would end up with 1.4142. And that's, for most of your calculations, the 4 decimal places will give you sufficient accuracy for what you're doing. Can't guarantee it always will, but in most cases it will. We're going to take a couple more like that to kind of get the idea. See, 2 is not a perfect square. There is no number that's a fraction or a whole number or a non-repeating decimal that you can multiply times itself to get 2. And I believe you're going to, that every square root of any number that is not a perfect square is going to be irrational, I believe. Yeah, 11 or non-repeating go on forever. That works out to 3.316622479. And if you did this with your calculator, it would fill up your display. It would put some rounding into the last digit. If you did it by a manual method of extracting a square root, you'd be working on that problem to eternity, because you keep finding more and more. You would never run out of anything to indicate the problem was finished, because it wouldn't be finished. And again, we'll use that wavy equal sign, equals approximately equal to. We'll round this to 4 decimal places. 3.316. That was 6 for the fourth one, and 6 here, so we're going to round that to 7. We round it up because it's greater than 5. So in the real world, when we're working with numbers that are not perfect squares and finding their square roots, we're usually going to be using an approximation, and these 4 decimal places is generally a close enough approximation for what you might be doing. We'll do one more. Square root of 15. And if we punch that into your calculator, you're going to get something like 3.872983334. And it'll fill up your calculator, but right in the last digit. But again, if you were doing a manual extraction of square roots, you could work on this problem for eternity, because you'd never be finished. You could make more and more and more digits. And we will use the approximate, and we'll round that again to 4 decimal places. We'll write down the first 3. 3.872. And we'll make a decision on the... I only wanted to round these just to 4 digits. I didn't want to round them to 4 decimal places. There's a difference. 4 significant digits is what I wanted to do here, because 414. Here the 316 rounds up to 7. And when we rounded this to 4 digits, we look at that 3rd digit. We see the 9, it rounds up to 3873. Depending on your need for precision, you may be carrying them out further, but This gives you to the thousandth place in this case. It usually will get you close enough for what you want to do. I'm going to erase that and remember that it's not a perfect square. A few more examples here just to kind of help one remember what the square root of 5 squared. Well, we undo the square root undoes the squaring, so we end up with 5. The square root of 3 squared over 7 squared. Again, the square root undoes both of these squaring, so it ends up being 3/7. And the square root of, well, it's kind of the same problem here, written in a different way. Here we've written it with the exponent outside of this parentheses. Well, here we've got the exponent moved inside, but again, that's, we got the square root undoes the square, gets you back to 3/7. So square root undoes applying a power to, or what we call squaring a number. We're going to do a few rules for square roots. And this is when the rules for roots, we'll call this. And we're talking about square roots in this case, but it's going to apply to other roots as we go further along. Basically, if x and y are both greater than 0, well, the square root of xy, the product of xy, is equal to the square root of x times the square root of y. We can put parentheses around the square root of x times the square root of. So those are our two factors, square root of x times square root of y, which of course square root of x, square root of y. There you go. Or if it's a product, the square root of x over y is equal to the same idea, the square root of x over the square. And I think we've done some of those already. We're more formally defining it here. So now we're going to do a couple of problems, and we're going to try to work them out with our calculator, and we're going to take advantage of these rules here. So we're going to start with a number, the square root of 12100. Now that looks pretty tough, right? But we can do this without a calculator quite easily by factoring inside into perfect square factors. That becomes the square root of 121 times 100. And you notice those are both perfect square factors, 121 and 100. So we can separate that to the square root of 121 times the square root of 100. And we'll take this down a little bit. Well, what's the square root of 121? The number that we square to get 121, which is 11. And what is the square root of 100? It's the number that we squared to get 100, which is 10. So 11, and we use parentheses to indicate multiplication, basically equals 110. And if you punch that 110 in your calculator and square it, you'll find that 110 squared is equal to 12,100. Let's put a comma there. So this looked tough to look at. We separate into perfect square factors. Then we broke it into two square roots. We utilized this top rule, the square root for products. And then we found those square roots, and then we multiplied them out, did the product of the square roots, and there we are. We had the result. And we got another one here. We'll do the square root of 441. Again, that one looks tough. But if we factor it, we'll find that that becomes the square root of one. This is a 9 and 49. If we factor that 441, now we've got it into two perfect square factors. So we can rewrite that square root of 9 times the square root of 49. We factored it. Now we broke it apart the way that we did here. Here's the factoring. We broke it apart. This was already factored x and y, but we factored it to 949. We broke it apart like we did with the products. So square root of 9 is 3 squared is 9, so that's 3 times 49. Square root of 49 is 7 squared times 7. That equals 21. So this looked a little rough. Factored into perfect square factors, which made it easy for us to complete that without even using our calculator. Now you could have punched into your calculator and had the answer quickly, but this is about understanding how it works. We're going to do one more like that, same kind of thing. The square root of 225. Again, that don't look so easy to look at it right away, but 225 can be broken into a couple perfect square factors, which makes it a little easier. So that's 25 times 9. 9 times 25 equals 225. So this is the same. This is basically the same number as that number. We've just factored it apart. But now we know that these factors, the square root of factors, is equal to the product of the square root of the factors. The square root of the product, xy is a product, is equal to the square root of the factors, the product of the square root of the factors. The square root of product is equal to the product of the square root of the factors. There you got a product. Here is the product of the square roots of each of those factors. So we can break that to square root of 25 times the square root of 9, which square root of 25, that's a perfect square, easy to do. It's 5 times 9 is a perfect square, easy to do. It's 3. That equals 15. Now, you know, so each of these that we did were perfect squares. They come out with nice whole number square roots. And some of them, you know, you might have recognized that 225 was 15. But by breaking it up, if you did not, you're able to do it by utilizing these smaller numbers. We're going to simplify a couple more products in a similar fashion here. So here we're kind of going to go the other way. The square root of 0.2 times the square root of 3.2. Remember, before we had the square root of xy, which we broke. I'm going to write that again. I'm going to write that back up here. Square root of xy equals the square root of x square root of y. So here we're kind of going the other way. Before we started here and went that way. Now we're going the other way. So let's combine those underneath the radicals. Neither of these are easy perfect squares, but we can combine them. The square root of 0.2 times 3.2. We do the multiplication, and we end up with, we're looking for the square root of 0.64, because 0.2 times 3.2, doing the whole 2 times 32 is 64. 1 decimal place, 1 decimal place, 2 decimal place. That takes us to 0.64. But now this one, that looks like a perfect square. 64 and 8. Well, we can use the 8, but we need, because we have 2 decimal places here, we need 1 decimal place in our answer. So that equals 0.8. So we found, taking this thing, by putting it back together, we got to a perfect square, which was easy for us to do. I mean, it was a perfect square. Well, these are not perfect squares. But when you put them together, we got a perfect square, and we were able easily to find that 0.8 times 0.8 is 0.64, which is 0.2 times 0.32. So the square root of 0.2 times square root of 3.2 is 0.8. We'll do another one like that. And I think you're probably starting to see why I put this x and x squared, the numbers and the perfect squares up there. So perfect squares on the bottom, square roots on the top. We've used that quite a bit in this lesson here. Now here's a little more complicated one. 5 times the square root of 125 times the square root of 5. Now 125 and 5 are not perfect squares. 5 is in, we're going to leave that in the form 5. So we're going to rewrite, we're going to put this product of roots and go back to the root of a product. Here's the product of roots, here's the root of a product. So we're going to put our radical sign here, and inside we're going to put 125. Oh, we got to leave that 5 up front. I'm going to erase that and make a little more room. We're not doing anything with the 5, so we're going to keep the 5 just like it was. Then we're going to put our radical sign. Inside we're going to put 125 and 5. So there we've taken this, which is equivalent to the square root of xy, same form. We've combined them to the square root of the product. This is the 125 and 5 inside underneath a single radical sign, which is 5 times the square root of 625. When we multiply the 5 times 125, we get 625. We don't have it up here, but the square root of 625 is equal to 25. If we'd have went on all the way up 25, we'd have found that we had 25 in our root or number row, and we'd have had 625 in our squared, perfect square row. So we can rewrite this. We can replace this 625 with the 25. 5 times 25, which of course we multiply equals 125. So we're presented with this, which looked a little tough. We combined it underneath the single radical sign. We multiplied out, got 625, which is a perfect square root. We took the square of 625, we replaced it with 25, and then we did the multiplication, got to 125. So we've simplified, we were able to do that without using a calculator by taking advantage of this square root. Product of square roots is equal to the square root of products. Or the square root of products is equal to the product of square root, whichever way you want to look at it. Product, of course, means multiply. Now we're going to do a couple of the ones that have division involved. So we're going to do the square root of 36 over 25. Well, we break that down to square root of the numerator, square root of 36, over square root of 25. Now these are both perfect squares that we find up here. So we can replace the square root of 36 with 6 right there, and the square root of 25 with 5. So we end up with 6/5. And if we divide it out to make a decimal, that's 1.2. You see how much we simplified it by breaking it to the numerator and denominator, which happen to be perfect squares, made it really easy to do. Okay. Now this one we're going to do a little bit differently. Same kind of thing, but we're going to do a little bit differently. So instead of going, we had our rule that said that we're going to rewrite our other rule for division up here. Square root of x over y is equal to the square root of x over the square root of y, which we utilized for this first part. Square root of x over y, and there's the square root of x over square root of y. We worked it out. Now we're going to go the other way. We're going to put those underneath it. look, think about the 3 and 27. Can you kind of maybe see why? Do you see something that could be done if you said 27 over 3? Well, let's just do it. Square root of 27 over 3. So we've taken this rule and went that direction. But notice that 27 is divisible by 3. So we can simplify this fraction. That's the square root of 9, isn't it? 3 goes in 27 9 times. And now we have a nice little perfect square, which equals 3. So we're able to do that guy. Yeah, it looked a little tough at first. We combined it, then we simplified the fraction. We simplified it to a perfect square. Made it pretty easy to do at that point. I think we're going to do one more and probably call her good for the day. This one's going to look a little rough at first. This is under the single radical sign of fraction, 0.5625 over 0.0625. We're going to utilize this part and break it into a square root of a numerator, square root of a denominator, which is the square root of 0.5625 over, get that decimal point so you can see it there. I'm going to erase that and rewrite it so the decimal point is more visible. 0.5625. Got to get my radical sign underneath there. 0.0625. Okay. So we've got here, and this one you're probably going to want to use a calculator to do, but it still demonstrates the way things break apart. We've taken the square root of a quotient or division problem, like here, square root of x over y. We broke it into the square root of the dividend over the square root of the divisor, or the square root of the numerator over the square root of the denominator, just like we see up here. And you notice these both have 4 decimal places, so we're going to have numbers with 2 decimal places for our square roots. Well, the square root of 56.5625 happens to be 0.75, and the square root of 0.0625 happens to be 0.25. Now we can multiply them both top and bottom by 100 to get no fractions, to get whole numbers in our fraction, which becomes 75 over 25. And if we simplify that, that simply equals 3. Now you could have punched that into your calculator and so on and did things, but this is an idea, is showing you how it breaks things apart to help you understand what happens. We utilize our quotient rule or our fraction rule, took the square root of the numerator and the square root of the denominator, we separated them under 2 different radical signs where we kept the fraction bar, that has to stay in there. Then we did the actual square root of the numerator to get 0.75. We did the actual square root of the denominator to get 0.25, which is probably easier to do those on a calculator, but you could, you could mess around. You could say 50 times 50, well that's 25. 60 times 60, 3600, that'd be big up. 80 times 80, that'd be 6400, so we're getting too big. You could narrow in on it that way if you wanted to too, but probably easiest just to use a calculator here for doing these 2 things. And now we have a fraction that's starting to look a little simpler, isn't it? And we multiplied top and bottom by 100, multiplied the numerator and the denominator by 100, or what I like to call a fancy 1. We didn't change the values, 75 over 25. Then we did the actual division, reduced the fraction to the whole number of 3. Anyway, I think that's probably enough for today. And I recommend you find some kind of a book to get practice problems on. We do problems up here, and I'm hoping you can follow what we're doing, but more practice helps you remember, and mathematics requires practice to get it firmly ingrained into your head. Anyway, thanks for coming, and until the next time, keep on learning.